Okay, so a little quick review of right hand and left hand limits. So remember I said the definition for a right hand is basically if you take your right finger and you're tracing along the curve until you get closer and closer to that x value. It's whatever y value you're getting closer and closer to. So this first one says the limit as x approaches 0 from the left. So as we're taking our left finger and we're tracing along the curve towards 0, we get closer and closer to the y value of 3. But as we go towards 0 from the right, that means we're plugging in like 1, 0.05, 0.01, 0.001. So we're going right here, getting closer and closer, and it's getting closer and closer to 1. So when it asks for just the plain limit as x goes to 0 in general, then we write DNE. It does not exist. So when we say limit as x approaches 5 from the left, don't get confused and think -5. That's the biggest mistake people will do on their homework. So 5 from the left is going to be 1, 2, 3, 4, 5. You're going to be like right here. So 5 from the left is going to approach the y value of 3. And then -2. -2 is going to be right here, so at a height of 3. And then 1 from the left approaches, right, we're going right there, we're approaching 2. 1 from the right is also approaching 2, so the limit as x approaches 1 is 2. And then limit as x approaches -3, 1, 2, 3 is 1. Okay, so we had all of those. And we talked about why f of 1 was different than the limit as x approaches 1. A limit doesn't actually have to have a filled in point. But when you say something like f of 1, that is a filled in point. Okay? So that was how we did it from just a normal graph. Oh, did we already do this one too? Oops, I was in the wrong spot. But can we sketch a graph? So this one says sketch a graph of an example of a function that satisfies all of the conditions. So we have the limit as x approaches 1 from the left has to be 2. X approaches 1 from the right has to be -2, and f of 1 equals 2. I always tell people to start with the actual points. So if you're given that f of 1 is equal to 2, then I would go ahead and draw in the point 1, 2. That one has to be a filled in point. Now, a lot of the things that you draw for these, I mean, yours might look completely different than the people at your table, right? So just know, like, they're not going to all look the same, but there are some things that are the same. So when we say the limit as x approaches 1 from the left goes to 2, it doesn't matter how you're coming into 2. You can go like that. You could come down like this. It doesn't matter, as long as you have a curve that is going towards 2. You cannot, however, as I've had people do before, just do like a big squiggle and do that. Why can this not work? Because it's not a function, right? Because it's failing the vertical line test. So make sure that whatever you're doing is still a function. So let's say we come down and we go towards 2. All right, so the next one. So the limit as x approaches 1 from the right is -2. So that means that I'm going to have an open circle there. It cannot be a filled in circle because then, like I just said, it would not be a function. It would not pass that vertical line test. So you can have it doing whatever you want it to do. It could do something like that, right? Okay, so the characteristics that you would look for is that you have a filled in circle here, you have an open circle here, and we approach from the right and the left towards those points, right? All right, so the next one says sketch a graph of the function that satisfies all of the conditions. So we're going to start with the ones that are equal, right? The f of 1 equals 1 and the f of 4 equals -1. So we know we have the 0.11 and we have the 0.1234, comma, -1. All right, so it says limit as x goes to 1 is 3. So as I go towards 1, from which direction? Both of them, right? So as I go towards 1 from both directions, it has to go towards 3. So that means I'm going to have an open circle at 1, 3. And from both the left and the right, I'm going towards that. All right, and then I have the limit as x approaches 4 from the left is going to be 3. So I need to be back at a height of 3 when I get to x equals 4. So it can do like a little hill or something to get back there. But it's saying as I approach 4 from the left, it has to go towards -3. Okay, so that's going to be this one. And then we have all of the things we need for our graph. So the portions of like the curves can look different, right? It's the points that all need to be the same. Okay, does that make sense to everybody? All right, so this one says determine the values of the following limits using tables and a graphing calculator. So go ahead and get your graphing calculator out. If you need an extra one, I have a couple on the front desk. Oops. And when you put this in, you want to do parentheses x minus 1 over parentheses x squared x plus 2 parentheses, right? So put that in for y1. And we're going to use the table function, which we used the other day. Yeah, what's your question?
Previous one, here's the graph was supposed to go as I was first for right -3.
Oh, did I draw the -1? Is it supposed to go to -3? Do you have a bonus point? Okay, so he's saying, oh, I did draw the negative. Oh, man, a bonus point. All right, good. So yeah, this is supposed to go to -3, right? All right, so something like that. Thank you. All right, Andy, write your name on the backboard so I don't forget, okay? All right. Okay, so we're going to do second table. And we're asking as we approach -2 from the left. So sometimes it helps if you draw a little number line and you think about -2. Does it say -2 from the left or right?
Right.
Is this one right? I just can't see it, guys. It's blurry on mine. All right, so as I approach from the right. So if I'm approaching from the right, then you want to plug in -1, -1.5, -1.9, -1.99, and you're just going to continue to get closer and closer to the -2. Okay, so on your table, let's plug those in. So we're going to do -1, -1.5. Whoops, I do not like me. Clear. Negative. Ah, I do this all the time. I always try to hit delete on the calculator. All right, -1.5. Enter. Gosh, I forgot my negative again. All right, so are you guys doing that? So as we're doing this, we get -2, -2.222, -8.033, -75.5, -750.5. Right, and if you want to see some of those other y values, like if I said round them to the nearest, or to like 4 decimal places, and you're like, but I only see 3 decimal places. What you can do, so everybody look up there, is can you see it? So you can move your cursor over and you can see along the bottom more decimal places. So if I ever ask for more decimal places that you can see, just move your cursor over. All right, so it doesn't really look like there's a pattern. Is it getting closer to something? Yeah, -infinity. So it's just getting really big, unbounded. So our answer is -infinity. So we did the -1, -1.5, -1.9, and so on, and it went to -infinity. So that means that the limit as I approach -2 from the right is -infinity. So if you look at the graph of this, so if I hit graph, oops, let me do zoom 6. Oh gosh, zoom 6. It does have some vertical asymptotes, right? So if you look, it's going to have vertical asymptotes at 0 and -2, and it goes down and then up and down, I believe. Is that what it was? Yeah, so what we're asking for as we approach 2 from the right, so it's this portion right here. So it's saying what y value do we go to? We go to -infinity. Does that make sense? All right, so let's try it on the next one. So when we do this next one, we're approaching, what is it, 2 from the left now? So again, if you need to draw a little number line, if you're approaching 2 from the left, you need 1, 1.5, 1.9, and so on. All right, and then you'll see that this one should have a vertical asymptote. If you factor the denominator, what does it look like the vertical asymptotes are going to be when you factor it? Yeah, 2 and -3, right? But it's actually not. Only one of those is a vertical asymptote. Yeah, just the -3. So this one's kind of a weird one because there's a hole. Okay, so if you hit graph, you can see that there is only one vertical asymptote. So as we do second table, we can plug in those values. So 1, 1.5, 1.9, 1.99, 1.999, and so on. So sometimes I would write 1 point and I would do 9999999, just do a whole bunch of them. Like, what does it go to? Right, and it actually gave me 0.4. If you do too many 9s, like if I just did it a whole bunch, it will probably say error because now it's just going to plug in 2. So see how that gets error, but if you do just the right amount, it will often give you the limit. So our limit should be 0.4, or 2/5. So let's see why that is true. So in the next section, we'll be doing a lot of this. But basically, if you factor the numerator and the denominator, you can see that there's a hole. Right? So our new function, like the one that we would graph, and then we would put a hole at 2 on, would be f of x equals x over x plus 3. Well, what do we get when we plug in 2 to that? 2 over 5, which is 0.4. Does that make sense? So there are ways to solve things like this algebraically without using a graph or a table, and we're going to learn that in the next section. There's going to be a lot of tricks for doing that. All right, and the last thing I want to talk about is the squeeze theorem. All right, I always like the squeeze theorem because when I was a freshman in college, my first math class was Calc 2, and I was in it with one of my roommates. And her name's Rachel, and she is from outside of Louisville, as she says. And she's from a little town called New Albany, and she has the worst Southern accent you've ever heard in your life. And so the teacher one day was like, yes, does anybody know what theorem I should use here? And Rachel raised her hand and she said, the squeeze theorem. Like very Southern. And he says, what was that? And so she raises her hand again and says, it's squeeze theorem, you know, the way she says it. And he goes, no, actually it's the squeeze theorem. And I just lost it and could not stop laughing because she had said squeeze theorem, but he could not understand what she was saying. So every time I see the squeeze theorem, I think of her. All right, so the squeeze theorem, or sandwich theorem, you can call it as well. There's a picture on the right. It basically says that f of x is less than or equal to g of x, which is less than or equal to h of x. So g of x is a function that is between two other functions whenever we're close to a certain x value. So in this general neighborhood, like around a, we are always, like the h of x is always on top, the g of x is always in the middle, and the f of x is always below. Okay? So it says, if the limit as x goes to a of f of x is equal to L, so as I get closer to the x value of a, f of x goes towards L from both directions. And g of x also, or not g of x, h of x also goes towards L. Then g of x is sandwiched between them. So what should the limit as x goes to a of g of x be? It should be L, exactly. Okay, so the most common things that we use these for when we're doing the squeeze theorem are functions that involve sine and cosine. Okay, because sine and cosine are sandwiched between two numbers. What is the highest value sine can have? 1. What is the smallest value sine can have? -1. So if we sandwich sine between 1 and -1, then we can do a lot of different things with it. So that's what we're going to do. So it says, use the squeeze theorem to show that the limit as x goes to 0 of x squared sine of 5x is equal to 0. Yes?
Theorem, it says when x is near a, how is near to
So when it's close to a, we would say a neighborhood. So you can make it as close as you want it to be. So calculus is very general about this. So basically, if it's within 1 unit, and maybe that doesn't work, then you make your interval smaller. You're like, okay, let's do half a unit. Does it work? Okay. And then also notice how it says except possibly at A. That means that one of them could be filled in, one could be open, one could be filled in. It doesn't matter if they're filled in or open or if they even exist at that point. All right, so here we go. So we have that sine of 5x. So it doesn't matter that we have a 5x in there. Sine of anything is going to be less than or equal to 1 and greater than or equal to -1. So it's sandwiched between those two things. All right. And we know with inequalities that we can multiply by positive numbers and our inequality signs do not change. Is x squared positive? Yeah, no matter what you have, x squared is always positive, right? So I'm going to say since x squared is greater than or equal to 0, we can multiply in. You don't have to write all of this, but we can multiply into this inequality. So we're going to multiply by x squared. So we're going to have negative x squared is less than or equal to sine of 5x, which is less than or equal to x squared. Okay, and now we think about limits. So we say, well, what is the limit as x goes to 0 of negative x squared? And what is the limit as x goes to 0 of x squared? So let's think about their graphs. If I have negative x squared, that's just a parabola that starts out at 0, 0 and goes downwards. And positive x squared goes upwards. So when I think about the limit as x goes to 0, I take both my right finger and my left finger and I trace closer and closer to 0. And what do both of them go to? 0. Oops, I forgot my x squared in here. You didn't tell me. Are you wondering about that? Sorry, multiply it into everything. X squared sine of 5x. Was he wondering? All right, so that means that the limit as x goes to 0 of x squared sine of 5x has to be what? 0 by the squeeze theorem. So for proofs, you always use like therefore, the little 3 dots. And then at the end of every proof, you'll see this a lot in textbooks. We always put like a little square, which means we're done. Did you even know we were doing a proof? That's a proof in calculus. Oh, wow. Remember proofs from geometry? We just did it. All right, so that's the end of that section. Good memories, bad memories?
I wouldn't repress them if they were good.
Oh, I didn't hear repressed. Ah, I see. Mr. T does make them very hard.